Well, that's the original problem, right? So it's not going to work, okay? But this right here at least has some road we might be able to go down. So ultraviolet, so these two multiplied first. I'm going to put the x in front. And then minus the integral of these two multiplied. So what I'm going to do is I'm going to take this x and put it on the top. Okay. Who sees how to do that? Basic U sub. Basic U substitution. Okay. So we're back to the method that, is an older method now. What would the U be? If you're going to do basic U substitution, what would the U be? 1 minus x squared. Good. So let's do that. So 1 minus x squared is going to be, so now I'm doing U sub, not integration by parts. I'm going to let U be equal to 1 minus x squared. The derivative of that would be negative 2x dx. X dx, I have x dx right there, right? So I'm off by a constant, so I'm going to scale both sides by negative 1/2, and that will turn this into the x dx. And now you can see that this matches up. So this is this, right? And then this is that. Now I'm going to do this on the side, okay? Because I'm eventually going to need to take this integral and get the answer and put it here. So I'm going to just do all this kind of over here, or maybe up there. So this new integral becomes integral, okay, everything in green becomes this. So I'm going to put the negative 1/2 on the outside du. That's the green part. And then I have the square root of the red on the bottom, which is the square root of u. So 1 over the square root of u. And then this becomes negative 1/2 integral u to the negative 1/2. I can bring the square root up and then just use power rule on this. So this will become negative 1/2 times, now the antiderivative of that, we add 1. That gives us a half, so we're going to have to put a 2 out here, u to the positive 1/2. These 2's go away. I have negative u to the 1/2. That's the square root, isn't it? Square root of u, but u is 1 minus x squared. See, I think pretty, yeah. So that is this integral, which is this right here. So now we come back and we get x inverse sine of x and then minus, because that minus right there, but our answer also had minus, didn't it? So it's really going to become a plus square root of 1 minus x squared plus c. There we go. Okay, how y'all feeling about this? Better a little bit? Yeah. So what I've shown you so far, the first one was a basic one, right? The second one showed repeating it more than once. Then I showed you one where it's not so obvious, but it works, right? And then I showed you another one where it's not so obvious where it works, right? But it works. All right. This one is a little tricky. Look at it, think about it for a minute. What are y'all thinking?
Make u ln x.
Make the u the natural log of x, okay. So can I ask why you want to do that?
It's not too hard to take the derivative.
Okay, right, derivative natural log of x. On a problem that I gave you before, right, that we did earlier today, when we did this one, I said, hey, you know, one of the things you want to see with the integration by parts is that we can chip away at this power, right? If we do it over and over, we can keep chipping away at that power. But there was a subtle thing there. Every time we chipped away, we had to integrate this, didn't we? And it was okay because the antiderivative e to the x kept on being itself. So it was okay. Just every time we did it, we brought the power down, and then this one, the antiderivative was fine. This problem is a little different. So you cannot get into the mindset of, oh, I'm going to start chipping away at the x cubed by letting u be x cubed, because you would have to integrate that antiderivative. And the antiderivative of natural log of x is actually complicated. We did it, right? I showed you what it was, and it required integration by parts to do it, right? So I think it was that Austin S?
Yes.
Okay, so Austin is saying, let's let the u be the natural log of x because the derivative of that's actually pretty nice. And that means we'll have to find the antiderivative of x to the third, which is going to wind up having x to the fourth. So we start to freak out a little bit thinking, wow, it's going to get more complicated, but it actually won't. Okay, watch. If we let u be the natural log of x, and that forces everything else to be the x cubed dx, then when we take the derivative of this, we get 1 over x dx. And if we do the antiderivative of this, we get 1/4 x to the fourth. So again, we're thinking voodoo now, right? Look at that diagonal. Are we going to be okay with this diagonal? Well, the 1 over x, all it's going to do is kill the power on one of those, right? And that'll just be x cubed, and I'm okay with that, right? So this is going to work. So this will become ultraviolet. So we multiply the 2 across the top, so I'm going to put 1/4 x to the fourth, and then natural log x. That's those two multiplied, and then minus the integral of voodoo, so it's 1/4 x to the fourth times 1 over x dx. So that's this multiplied. This becomes 1/4 x to the fourth, natural log x. And then I'm going to bring the 1/4 out, minus 1/4 integral of x cubed dx. And that one we can find the antiderivative of. Okay, the antiderivative of that is 1/4 x to the fourth plus c. So put those two together and get 1/16, and that should be it. Any questions there? So I guess the moral of the story here is that even though I want you to be thinking about how you can use the integration by parts to take a power and keep on bringing it down, sometimes it's better to go the other way. All right. We still all good?
For that one in between, how did we get a 3 there? I got a little lost right there.
Here, this one?
Yes.
Oh, just putting this together.
Oh.
X to the fourth, cancel out 1x. Any other questions? All right, the next problem I'm going to do is a classic problem. Okay, this is, everybody has to see this problem at some point in their life. For you, it's today. All right. I'm going to put it up here, and then I'm going to let you mess with it for a minute, see what you think, all right? Sine x times e to the x dx. Why don't I let you all play with that for, I don't know, 30 minutes maybe, 5, 10 minutes? Let's go 10 minutes. I'll give you 10 minutes to see if you can mess with that. And really try and see. Set up your integration by parts table, see what happens. And you're probably going to run into some issues, but let's just see, all right? And y'all can ask questions while you're right here. I can come around and take a look at what you're doing. You saw it?
Wouldn't it just be a loop?
What?
Wouldn't it just be a loop?
A loop?
Yeah, like go from sine to like cosine, like negative cosine.
Okay, so write it out. See, I mean, at least set up, do the integration by parts one time and write out what you get and then think about what you would do after that. I think you're right. I think a loop is possible here. Did you try it?
Trying.
Yeah. Let's see what you got. Okay. So antiderivative of that is itself, right? Are you getting something there? Yeah. Okay. Yeah, so just, yeah, there you go. So you're trying it again. Yeah. Okay, so you see you're starting to get yourself in. Yeah, just mess with it. Are y'all kind of seeing this loop that you're getting caught in? Yeah, okay. Yes, you got caught in this little loop.
Well,
Or you haven't done it yet, but you're just thinking through
I was
it.
in my head and I was
Yeah.
like going sine of x, like either
Yeah.
way it would just keep looping and then e of x would be the same thing.
Yeah,
over
yeah,
and over.
okay. If they cancel, what'll happen is you'll wind up, things will cancel and you'll get back the original integral. Like it'll just, and then, yeah, so. All right, so maybe we won't need 10 minutes. Like I said, this is a classic problem because of what y'all are seeing happening. All right? So I think what I'll do is I will go and ask for a volunteer here to tell me what they used for their U and dV. So you did sine for your U? Okay. And then over here you did e to the x dx. Okay. Now some of you may have chosen to do e to the x here and sine here. It actually will work both ways. So let's see what happens. If we take derivative here, we get cosine x dx, right? Find the antiderivative of this. This is e to the x. All right, so we just do this. Turns into ultraviolet, these two multiplied. So sine x e to the x minus the integral of voodoo, which are these two multiplied, which is cosine x dx, e to the x dx. Okay. So you look at that, you say, oh, I can't do anything with that, so maybe do integration by parts again, right, on this. But this is where you're starting to think, like, wait a minute, every time I take derivative of cosine, I'm going to get back to sine. If I integrate e to the x, I'm going to be back at e to the x. It doesn't appear like anything's ever going to get better. I agree, but persistence, right? So let's keep going here. So this is important. What do we choose for u here? If you do the reverse of this, if you did the e to the x here and the cosine here, you're going to go right back to where you started, because you're basically undoing what you just did. So did you do cosine here? Okay, let's do that. Let's do cosine x here, e to the x dx here, and let's just run through it again. Okay? So du is negative sine x dx. And v here would be e to the x again. So here's what we got. This equals sine x e to the x minus, okay, this is important, minus this integral, right? We are going to set up using the integration by parts table right there. So I have a bracket and now a new ultraviolet minus voodoo here. So ultraviolet will be cosine x times e to the x minus the integral, and now voodoo, which is this, which is negative sine x, right, e to the x dx, and then close my bracket. And this is where you look at it and you go, crap, this is the original problem, right? And so this is where you're thinking like, okay, we're caught in a loop, right? We're not. So watch what happens here. This is really cool. That's why this is a classic problem, okay, that we show all Cal 2 students. Okay, so I'm going to leave this here just in case someone's behind here. Okay, this is going to be equal to, so watch, sine x e to the x minus, now what's in brackets, I'm going to distribute. Can we do this? Can we change this minus? That's going to become a plus, right? Now I'm going to distribute this minus through. So this minus is going to hit this. So it's going to become minus cosine x e to the x. And then that comes through to this integral, right? So it's minus this integral. Minus this integral, sine x e to the x dx. Does everyone see that? How these signs became what they are? Any questions? Sure? Everyone's good? That's the original integral, right? Okay, so watch. This is the part that's really cool. So this is what we're saying, right? What we're saying is that we have the original integral, right? The thing we're trying to find the antiderivative of, right, is equal to this. Sine x e to the x minus cosine x e to the x minus the integral again. The exact same integral that we started with, right? That's where we are? Okay, here's the cool part. Ready? Add this integral to both sides of the equation. Right? This is an equation, right? So this should be true. So if I add that to both sides, it goes away here, right? And now I have an apple plus an apple is 2 apples, right? So what we have now is that, I'll save myself some room. This plus this is going to be 2 of them, right? 2 of those integrals are equal to this. Sine x e to the x minus cosine x e to the x. That's just this part. And then divide both sides by 2. And we're done. So this will be equal to Well, let me do it this way. Divide by 2, which makes this have a 1/2 in front of it. You know what, I don't like that. I'll just write it again. I just didn't want to erase that yet. So here's where we are. Divide both sides by 2, you get the integral sine x e to the x dx equals 1/2 sine x e to the x minus 1/2 cosine of x e to the x times e to the x. Now, that was tricky, right? Like, that was weird. Because it's an antiderivative, we need to do plus c. Okay, we kind of lose that. Whenever we do this method, we kind of lose the fact that there's a plus c there. But that's kind of neat, right? I mean, it looked like we were going to be stuck in this infinite loop. But because the original integral appeared on the other side, we can move it over algebraically. Okay. Yeah. What do y'all think about that? Any questions at home? So some calculus professors, they teach something. I don't teach it. If you've heard of this before, I don't even know what it is necessarily. It's something like, I think it's Liate or something like that. Has someone heard that before? Seen that before? You have? Anyone at home? I don't know, is this right? I don't even know. Do you remember seeing something like this? So in Cal 2, some professors teach this thing, and I could be wrong. It could be wrong here. It's like anytime you see an integral, like when you're doing integration by parts, like what do you use for the u? This is saying use logarithms first, and then I don't even know what the rest mean. It's like, I'll have to look it up. I don't teach it because I don't like to teach things that don't require you to think about what's happening. I'd rather you say, oh, look, you know, if I do this the u, then in the new integral it's going to be this, and you're thinking about that before you're doing it. I think that's better for you than to just be like, always try the log first, then after that do this, and then that, and that. I think that's wrong, though. Yeah, okay. So what have we seen? Basic one. We've seen where we have to do it more than once. We've seen where it doesn't look like you have two things, but you know, the natural log and the arc sine one. Another one where we had the x cubed in the log, where you use the log as the u. And then this one where it just seems like out of nowhere, this thing loops around and then you can bring it to the other side. So lots of variations here for integration by parts. Okay, I did bring my book. Since I don't have my notes, at least I brought my book as a backup. There's a problem here I want to show you. Trying to decide how much time do I have. That clock's wrong. Still have 40 minutes. Does it seem like it's going by faster or slower this way for y'all? Slower? Me too. I'm like, I can't believe we still have 40 minutes. How about at home? I guess no difference, huh?
A little quick.
Seems fast? Don't tell us that. I think we're all going to want to go back home. All right. Yeah. Okay. You ready? We'll try this one. Yeah, so I like that reaction. Whoa, right? Okay, so the antiderivative of that is not just e to the square root of x, right? because chain rule, if you took derivative of e to the square root of x, would not give you back that. Okay, so I put this one up here because this is, again, another example of something where you just kind of have to see one of these first before you can really feel comfortable with it. I'm going to make a basic u substitution first. And that should kind of make you scratch your head. Like, a basic u sub? I don't see something in its derivative, right? Like, so why would I make a basic u sub? And really, it's because you don't have really anything else to try. So let me just so we can see it, if I tried integration by parts now, right, dv, sorry. If I tried this now, your only choice is this, right, like that. And then dx here, that's really, and then this derivative is going to get complicated. This is going to be 1. That's going to be a complicated thing because I'm going to have chain rule here. Understand? This is not necessarily something I want to just step into. Now, could it work? Maybe. Maybe. But I don't like the way that looks. So I'm going to do a basic u sub first. And the u sub I'm going to do is the square root of x. Now, why? Because I've got to try something. Now, I know that the derivative of this is 1 over 2 root x dx. That's just cal 1, right? Now keep in mind, this here will be replaced with u, won't it? That's going to be replaced with u. But look at all that, look at this complicated expression here, right? What we have here, the only thing really left to play with is the dx. So I need to figure out if I can get this dx by itself. The problem is I've got x's still, right? So even if I try and like isolate dx, this side's going to have u's and x's. However, what is the square root of x? Yes, but what is it? It's u, isn't it? So if let me do this. If I multiply both sides by 2 root x du equals dx, I can now replace dx with this. And normally I would tell you don't do this because now you've got u's and x's mixed up, don't you? But because this is u, this becomes 2u du equals dx.
Right.
Y'all are really starting to get a feel for why this Cal 2 is so much different than Cal 1, right? It's just not as, you know, point A to point B formula, you know. It's like you kind of wish you were doing chain rule now, right? Because it's just not so complicated.
Things are right there. I just don't see it.
Yeah.
You know what I mean? Like,
It'll come with time. That comes with time and practice, repetition. What you can't do is sit here and watch me do it and be like, yeah, I got it. Never practice, and then get to the test, and then you're like, I don't see it. It's that recognition comes with time. And there's so much to recognize because every problem is a little different, right? Okay, so I can rewrite this problem now, can't I? This whole problem can be rewritten in terms of u. So let's replace this first. That's integral, that's e to the u times the dx, which is 2u du. And I can pull the 2 out, e to the u du. There we go. Now this problem looks a lot like the first problem we did in class, right? What was the first problem we did in class today? Was it x e to the x dx? Was that the first one we did? Oh, it was x squared, right? Okay. But when we did x squared was the first one we did? Yeah. Oh, x sine. It was x sine 10x. That's right. Okay, x sine 10x. Thank you. But the idea there, I mean, it's kind of the same as this one. We can start chipping away at the power because the antiderivative of e to the x is just itself. So I have that same sort of format here. it's e to the u, and I have a u out front. So if I do integration by parts one time, then I'll be able to take that power on the u down to 1. It'll turn into a 1. And then I can integrate the e to the u, and it'll become e to the u. Understand? There's a little bit of a catch here, though. When I use integration by parts, I use u and dv, don't I? But see, I'm already using u in this substitution. So I can't use u and v again. Like, I can't use the u to be something else. That's okay. That's okay. Because what I'm going to do, right? Remember, this is what u is. I'm going to keep that up there because we're going to need u in a minute. What I'm going to do instead is I'm going to still set up an integration by parts table. But instead of calling it u and dv, I'm just going to use a different letter. So I'm going to use, how about w and dv? The thing that's bad about this is that you lose the whole ultraviolet minus voodoo. You lose that little thing because you're not using u anymore. But that's why I think the table's so important, because it's always going to be these two across, right, minus the integral of the diagonal. So it doesn't matter what these letters are. So what's going to be w? The u, right? And then the dv would be the e to the u du. And then we differentiate down. dw is du. And then the antiderivative here is e to the u. So this becomes the 2 out front, don't forget the 2. And the 2 is going to get distributed through to everything here. So this is going to become the kind of, what, it's not ultraviolet minus voodoo, it would be like yeah, forget it. You get the idea, right? It's these two multiplied, right? These two multiplied, u, e to the u, minus the integral of these two multiplied, which is e to the u du. I didn't even bother to check. My audio is coming through good, right? Yes?